So now I'm going to talk about the second case from the three cases we discussed in the previous lecture for dealing with these differential equations. Say you want a general solution to ax prime prime plus bx prime plus cx equals 0. So second order linear homogeneous differential equation with constant coefficients. And what we discussed last time is you should guess x equals e to the lambda t and then find out what lambda must do in order for this to work. And when you make this guess, it leads you to this situation, this what is called a characteristic polynomial. So you get this quadratic polynomial, and there are then three cases. So you either have you either have distinct roots, which we dealt with that case last time, distinct real roots, or you have repeated roots. That's the case I want to deal with now. Or you have complex roots, which we'll start looking at the idea today, but we'll actually deal with it next time. Okay, so right now in this video I want to focus in on the repeated roots case. So repeated roots means when you looked at this polynomial, it ended up being a square. So like, I don't know, something like something times lambda plus something all squared. So it ended up being like that. So you've got this equals 0. Then there's, you get two solutions, but they're the same solution, right? Lambda equals this, lambda equals the same thing. So what do we do here? Let's say your repeated root is lambda. Let's just call it lambda instead of saying lambda 1 or lambda 2. Say lambda is the repeated root. Well, then e to the lambda t, then definitely x of t, since lambda is a root, definitely x of t equals e to the lambda t is a solution to the differential equation. But taking linear combinations of just this, so let's call this x sub 1, taking linear combinations of just x sub 1, like c times x sub 1 of t, that would give you just a one-dimensional space of solutions to the original differential equation. And that is not enough. That's not enough for satisfying or for solving arbitrary initial value problems. So we need more. Okay, so this is x sub 1. Need another solution, x sub 2. And then if we got another solution, x sub 2, then we could write our solution as c1x1 plus c2x2, right? That's the idea. But x sub 2 needs to be another solution, and I cannot just repeat this one as suggested by the fact that lambda is a repeated root. It would be a bad idea to say x2 is just this one again, because that would not be linearly independent. So we need another, by another I mean another linearly independent solution, x sub 2. So something else is needed. Some more work is needed, I mean. Okay, so this is, you're going to hate this. I'm just going to tell you what it is. So I'm going to tell you the answer. Use x sub 2 of t equals t e to the lambda t. Just take your x1 and multiply it by t. And this will work every time. Every time you're in the repeated roots case, this will work. So no matter what a, b, and c are, as long as they are such that that polynomial is a square, so you're in the repeated roots case, this will actually work. And I mean, this is a math course, so I should convince you that it works, right? Well, I can convince you that it works. That's fine, but you're still not going to be satisfied at the end. So let me just convince you that it works. So suppose a lambda squared plus b lambda plus c ended up being a square like this. So let me pull out the a overall. So let me write a. Personally, I find it easier to write down the square of a polynomial with leading coefficient being 1. So suppose it ended up being a times lambda minus, well, this is confusing. I'm using lambda for the variable and for the repeated root. How about I call the repeated root lambda naught instead of just calling it lambda? Lambda naught. Lambda naught. So let's suppose we ended up with a times lambda minus lambda naught here. So this is what it looks like when you get a repeated root, right? The polynomial ends up being a square. Then I claim, then I shall convince you that t e to the lambda naught t is a solution to the differential equation. So let me convince you of that. And you should already be convinced that e to the lambda naught t is a solution, because, I mean, demanding that that be a solution is how we got to the idea in the first place that these roots, that we want these roots in the first place, right? So this is where I still need to convince you of that something is going on, that something good happens. All right, so how do I convince you? How about I just plug it in and see that it works? So I'm just going to take the original differential equation, ax prime prime plus bx prime plus cx, and then plug in this. And this is going to be kind of boring, so I'm going to skip over some of the calculation parts. So let me just write, if x of t is te to the lambda naught t, then x prime of t, okay, so I have to use the product rule, and I get this. So x prime prime of t is lambda naught e to the lambda naught t plus, and then I have to use the product rule again now on this, and I get this, which is this. Okay, and now I'm going to put it into the differential equation. So then ax prime prime plus bx prime plus cx is, then I just have to stuff this in there, and I get this. So there's ax prime prime, so I just copied this over, and then b x prime, so I copied over x prime, plus cx, and I seem to have left out the c. Now, if I can show that this comes out as 0, then we'll be done with the proof. We will have shown that this is a solution to the differential equation. So the goal is to show that when I do this, I get 0, right? Okay, well, as far as functions of t are concerned, what I've got here is basically two different functions of t. E to the lambda naught t and t e to the lambda naught t. So I'm going to focus on writing, stuff times e to the lambda naught t plus stuff times t e to the lambda naught t, and see if I can show that the stuff on either side is 0. The reason I'm focusing on doing it this way is that I know that e to the lambda naught t and t e to the lambda naught t are linearly independent, which I have not yet convinced you of, but it was the whole point, actually. We need to get another linearly independent solution. So if these were not linearly independent, then I would have failed already. But we'll discuss that in a moment. So right now, let's just see that it is a solution. So let's see. So what goes here? Let me just do this off screen. Okay, there we go. I filled it in. So this 2a lambda naught is coming from a and 2 lambda naught here, and this b is coming from this b here, which is, those are the two things that get multiplied by e to the lambda naught t, which you see here and here. And then for t e to the lambda naught t, you've got a lambda naught squared, so that's here, and you've got b lambda naught, so that's here, and you've got c, that's here. Okay, again, my goal is to show that this is 0. Well, this one is definitely 0, right? This is 0 because lambda naught is a root of the characteristic polynomial, right? So that's what we mean when we say lambda naught is a root. Lambda naught is a root means a lambda naught squared plus b lambda naught plus c is 0. So this is 0. What about this one? 2a lambda naught plus b? Is that 0? Well, if lambda were a repeated root, as we're supposing that it is here, then this polynomial must equal a times, and then let me square this. So this would be lambda squared plus 2a lambda, sorry, plus 2 lambda naught lambda minus 2 lambda naught lambda plus lambda naught squared. So that's what you get when you square this binomial. And then we're saying, okay, and then I can distribute the a lambda squared minus 2a lambda naught lambda plus a lambda naught squared. We're saying that this is the same as a lambda squared plus b lambda plus c. Now, polynomials are equal if and only if the coefficients are equal. So this a has to match up with this a, which it does, and they're both a. And this a lambda squared has to actually match up with this c. So that tells us that a lambda squared equals c. And this minus 2a lambda has to match up with this b. So that tells us that b equals minus 2a lambda. But look what we have here. This is b plus 2a lambda. So since b is equal to minus 2a lambda, lambda naught, sorry, 2a lambda naught, the minus 2a lambda naught matches up with the b, then this must be 0. So our calculation, when we plug in x equals t e to the lambda naught t in for x in this expression here, ax prime prime plus bx prime plus cx, we get 0 plus 0. So we got 0. So then t e to the lambda naught t is a solution. So this should convince you at least that t e to the lambda naught t is a solution to the original differential equation when e to the lambda naught t is a solution, and when lambda naught is a repeated root of the characteristic polynomial. This only works when it's a repeated root, because we needed to match up the b with this thing to get our 0 back there. Okay, so that's that. Oh, well, I guess I still need to convince you that it's linearly independent, which I will do in a moment. But I just want to preempt the next question. Probably at this point you're still not satisfied and you're thinking, well, where did this come from? What are you doing just giving us the answer? So the answer comes from some linear algebra way of thinking about this. One that we haven't discussed, so we're definitely using linear algebra already in our discussion, but there is a way to convert these second order differential equations where there's one unknown function, x of t, into first-order differential equations where there are two unknown functions, like x of t and y of t. Those kinds of differential equations, first order but two unknown functions, we will study those in chapter 4. And when we get there, then if you write things down using the linear algebra language that will be available then there will be a way to motivate where this times t comes from, maybe. So save that for later. And if you're unsatisfied by this, that's okay. Remain unsatisfied. Okay, now what I still need to convince you is that this really is linearly independent. So let's look at that. So I'm going to convince you that these are linearly independent. So suppose that, so I hope it feels intuitive to you that they are. If C1 e to lambda naught t plus, if this is 0, it should feel like C1 and C2 have to be 0. Or maybe that here it is in a more intuitive sounding way, I think. For these to not be linearly independent, for there to be a linear dependency, it would have to be that one of these vectors is a scalar multiple of the other. Do you feel like that's possible? Do you feel like it could ever be that e to the lambda naught t is just a number times t e to the lambda naught t? It should feel wrong. That doesn't feel right. They're very different functions. They have very different behaviors. You wouldn't expect to be able to get from one to the other by just multiplying by a number. So I hope that feels right. And then now for just establishing it once and for all that they are linearly independent, suppose that you've got a linear combination and it ends up being 0. Can we verify that C1 and C2 have to be 0? So this needs to be true for all t with the same C1 and C2, right? So we're going to use that. So I can plug in any specific value of t that I want to try to get specific results. I'm going to choose to plug in t equals 0. So at t equals 0, we have, and I'm only choosing this because it gives me a nice simple equation, we have C1 times 1 plus C2 times 0, right? If you plug in 0 here, equals 0. So in other words, C1 equals 0. So then, going back to our original statement, overall we've got C1, well, C1 is 0 now, so we've got just this equals 0. C2 t e to the lambda naught t equals 0. And can I verify that C2 also equals 0? Well, how about we put in t equals 1? At t equals 1, we now have C2 times e to the lambda naught equals 0. So, well, e to the lambda naught is definitely not 0, right? Exponential of something is never 0, so we can divide both sides by it, so C2 is 0. Okay, so these are linearly independent. In the next video, I'll show you very quickly an example of this idea and how you might use it to approach an initial value problem.